Works. It's looking okay at the moment. Oh, no voice today. Right, I've got sound, I've got image. I think it's recording everything. We've got full frame rate, no dropped frames. This is looking good. So yes, I'm just testing out my new streaming setup. I've put Linux onto my streaming computer because I was fed up of blue screens. So now it's all Linuxified. I've spent the last day sorting it all out, fixing it all up, installing all the software, setting up all the scenes, all that sort of rubbish. And I think, fingers crossed, I've got a nice stable system now, and better than before. So yes, I'm testing it out, and I'm just going to tinker with some Logisim stuff that I've been working on. Let's switch over to, there we go. That's my main computer. I've got Logisim on the left, I've got a schematic on the right. And what I'm doing is creating 7.4 Logic series chips in Logisim. It has a whole load in there already, but I don't like the way they've done them. They've done them as I can't do it in that view, can I? They've done them as actual chips, which I do not like. For example, the hex inverter, it gives you a chip. Yes, you can sometimes see the actual layout, but unless you've got the data sheet in front of you, you can't see what pin is what on that at all. So I'm going through and creating a whole load of 7.4 Logic series as a library using the actual layouts from the datasheet. They function properly, and give them a proper pin layout, so you can see what pins are what and connect them up properly. Some of them have come out like this, some of them like this. I'm not sure which style I prefer, actually. They're both auto-generated in Logisim, so it's easy to switch. So yes, I've got this schematic, which I've got to sort of reverse engineer and diagnose and work out what's going on with it. So my first job with that is to make sure that I've got all the logic chips that I need. So I'm just going through each chip on here, making sure that I've got it in my little library here. And if not, create it. So my current one of interest is the 74158, which I don't have at the moment. I've got the 157, this one here, which is sort of the opposite of the 158, I think, isn't it? The multiplexer, the 158 is the demultiplexer. Oops, come back. That's the one I want. So 74158. Let's get a data sheet for that first. Open that. 74158 is the quad 2 input multiplexer inverting. Right, so it is a multiplexer rather than demultiplexer, but it's inverting. So that's pretty much exactly the same as the 157, but without these inverters on the end here. So that's an easy change. I'm just going to copy the whole lot there, add a circuit, SN74HC158, and paste it. Take out these. inverters and replace them with buffers. No need for these buffers to be there really, but they're in the schematic, so I'm having them. Okay, hook these up. That is... select on this is inverted. Hang on, have I got that right on the other one? Come on, there we go. Move that across, take that out. Let's put an inverter in there. Okay. That is the same. Let me just check the 157. Not sure that I've got that open at the moment. No. 74157 I had here. And oh yeah, there is a, is that right? Yeah, that's non-inverting that is inverting. And that's, oh, hang on, these are also reversed. Okay, different implementation of the same logic, just gives you a different order of pins on the 158. Circuit layout. So these are, actually I could, no, I will keep it the same as the schematic. That's, right, let me do that with it. No, it's going to be A0 there and A1 in there. Let me do that. Let's change these. C2, D2. E0, C0, and E0, E1, C1, and D1. Okay. Edit the appearance, switch to that mode. There we go, I'm happy with that. Okay, that's 157 and 158 we've got. 373 I have. 157 I've got. 139 I've got. 08 I don't have, but that's just a basic AND gate. I don't really need to create that. 138 I've got. 138. 74 LS74. That one I need to create. Yeah. Logic diagram for one flip-flop. What on earth is all that weird stuff? I don't recognise that logic symbol. Uh, 74HC, let me just create the circuit. 74HC74. Let's Put that letter at the beginning before I use SN. Right, and CP has a Schmidt trigger on it. And we've got all this weird stuff. This is a D-type flip-flop. I have a basic D-type flip-flop that I've already created. The CP. This has got SD and RD. Set data and reset data, which I think is pre and CLR. So I can probably do this just with two of these. I hope. I don't know what these purple boxes are. It keeps sticking all over everything. It's a bit of a bug in Logisim. It is Java after all, so what do you expect? So we've got nothing really to do with this other than just wire these up. Should be nice and easy. This goes in there. That into there. That to there. Okay, now they call these pins. Where's the actual pin layout? Yes, one RD, one D, one CP. I'm going to have to reverse those. Because in Logisim, a pin can't start with a number. So let's just have a west-facing foot. Let's move these in a bit. Two outputs on each. So pre is 1 SD, which will be SD1. D1, CP1, RD1, SD2, E2, CP2, and RD2. And then we've got Q2, Q2N for negated. Actually, that was wrong, completely wrong. Q1, isn't it? Q1N, this is Q2. Q2N. Right, that should be enough. Save that. And edit the appearance. Switch to that mode. That's good. Might bring these down actually. Oops. Select it all. Come on, and those. Okay. Don't let me do it all at once then. No, not going to do it. There we go. Do. Okay, that's that one done. What else do we have? 74LS670. Ooh, that one I definitely don't have. Okay. This one is a 16-bit register. Okay, organised as 4 words by 4 bits each. Read and write address and enable inputs allow simultaneous writing to one location while reading another. That's chips. 4 data inputs are provided to store the 4-bit word. Okay, this could be tricky to implement. They don't show a diagram for this one, of course, do they? Nope. Just a functional diagram. So we've got 4 bits in, 4 bits out, 2 addresses. Read address, write enable, read enable. So I'm thinking SN74HC670. If I had a simple D type with a controlled buffer on the output going to no, what I want to do actually, let's simplify this. Let's add an XX for but no, both 4x reg. It's 4 hyphen reg. Have a hyphen in it. XX4 reg. Do. Right, let's just make a generic 4-bit register using 4 D-type flip-flops with a controlled buffer on the outputs. Yes, I want a pin in there, don't I? Which wants to be west facing, and output and tri-state. That is just U0. Four of those. Q1, Q2, and Q3. And then have a global output enable. E. Actually, I'm going to add an inverter into there, I think. So that it's active low. Okay, so that's output enable, which will give me the output of these through the queues. Then I need 4 inputs. Going to the data. Okay. kind of, oops, missed the pin there, didn't I? Get that out. Okay. So I've got D0, D1, D2, and 3. Okay, now I have clocks all tied together. Which goes to another pin, which is write enable. Possibly. I'm going to have to test for this one, aren't I? Okay. Let's save that and edit the appearance. Give me that. Okay, let's make a new test circuit. We'll put in the reg, and we shall have a pin for each queue. Okay. A pin for each input. Okay, and let me call these up. Okay, if we turn on OE, nothing happens on the outputs. That's not good. Undefined. Okay, let's have a look. What's happening here? Why are things... of course, simulation isn't running. That's why. I'm an idiot. Okay. So output enable is active when low. That's good. I'm not getting anything from the writing though. Why not? Is it because these are floating? I can't remember. The flip-flop is looking like this. And I've used it somewhere else. Where did I use it? In here. Where I've connected 3 to 1 and clear is on an input, so maybe I need to connect that up. So let's take all the pre's up to a 1. And I need a constant 1. So facing. Okay, so let's go into poke mode and poke that. And that goes, it modifies the output there. Okay. So when write enable is high, I'm getting pass through. When write enable is low, I'm not getting anything passed through, but I'm not getting any output either. Is that because clear is floating? Let's bring clear down here. No, I'm not sure whether I want that to be a 1 or a 0. So let's give it a 1 initially. Go back to poke mode. That's better. So write is active high. When write is high, data passes through. Lower it and no, there's not right. Oh, clear is not connected there. That's why. Connect that to there and that to there. Okay. When write is high, data passes straight through. When write is low, it keeps the previous value. So really I want to invert that because on here write enable is low. So let's put in an inverter here. Okay. Save that, go back to my test. So poke mode would help. Let's toggle write enable. And I've got things wrong going on here. Is that because this needs updating with a new version? That pin there. Well, I accidentally deleted it. Okay. What's going on here? Let's refresh that as well. Shouldn't make any difference. Oh, it's this stupid bug leaving stuff in. Let's move this down. Put this in fresh. Okay. So let's say undefined even when. What's going on here? I always forget that, don't I? Okay, back to Run the simulation. Oh, that's what the pink stuff is. So output enable, nothing happening there. Why is that red though? Um, okay. Looks like it should be fine. Oh, right, that's working now. Okay, so output enable gives me those ones. I turn those off, pulse right enable. That gives me that value. Excellent. Right, that looks like it's working. So if I go back to the 670, let's get into design mode, shall we? I have 4 of these registers. And I have 4 input pins. For the 4 data pins. Those go through to all 4 of them. E2. And D3. Okay. The same with the output. Let's send that to be west. Output 3 state. 2, 3, 4 of those. Oops. Connect all the outputs up. Go one more. Q3. There. Okay, now the trickier part is the write enable and read enable. So now we want which one is it? 139? Yes, we'll go for 74139. Let's pop that down here. Use A as read as write and B as read, I think. Read is I don't know, I keep it the same way up as this, I think. So I'll have A's as reads and B's as writes. Keep it easy to follow. So I want these in here. Let's move this over. So this is RA0 and RA1, WA0, WA1. Now reads, let's take the output enable for these and bring it up to these output enables here. That should be all that's needed for these. Go the right way. Okay, and the read enable should be a pin here going into that enable pin. That's read enable. That's looking good. Enabling each one in turn. Yep. And then I do the same with the right pins. Put those onto the B channel. And that should do the same job for right. Yep. With a pin, which is right enable. Let's just name these D0 to D3. And these Q0 to Q3. Right. So if I put 1010 into address 1, clear that out, and then I read address 0, there's nothing, read address 1, 1010, read address 2, nothing, 3 zeros. Yeah, perfect. I think that works. So edit the appearance and make it look like that. Loop. Right, that's that one done. I think we might be almost there. 138 I've got, haven't I? 138 I've got. Another 74, 74, 175. I don't have the 175. I've got the 157. That's 4 Ds, isn't it? Add a circuit. 7 48175, which I believe is just 4 D-type flip-flops. Which is kind of the same thing I've got for the 4 edge there, isn't it? But yeah. It's got a master reset, which goes to clear. Pre doesn't go anywhere, so I'm going to start off with a constant 1 for pre. I've got 4 Ds. We've got 1 common clock. Okay, and 1 common clear. Shorten these a bit. Okay, what have we got? Pins now. I'm just going purely by the symbol on the schematic as to what this chip actually is. I've not looked at the data sheet, obviously. I guess I should do really, but yeah. Okay, west facing. It's pretty obvious what it is. You've got D's, Q's, clock, master reset. It's obviously a quad D. Okay, connecting those up and take the whole lot together. Okay. So we've got Q0, Q0 negated. Oops. We've got Q1. We've got Q1 negated. We've got Q2. We've got Q2 negated. And we've got Q3 and Q3 negated. D0, D1, D2, D3. The clock, and we've got reset. That's good. Okay. What else have we got? Is that all of them? The only one that's missing now is DRAM chip, which that's not going to be easy to implement. Do I really want to implement the entire thing? I mean, got have a RAM block. Which I could use for it. But that's that's static RAM, you see, 256 by 8. Whereas this is dynamic RAM, and 64K by 1, or 256K by 1. 4164. 4164 RAM. Still sell them at Farnell apparently. So we have, because this is 64K with 8. 16 address bits are required to decode one of 65536 storage cell locations. 8 row address bits are set up on pins A0 through A7 and latched onto the chip by the row address strobe. Then the 8 column address bits are set up on pins A0 through A7 and latched onto the chip by the column address strobe. All addresses must be stable on or before the falling edges of RAS and CAS. RAS is similar to a chip enable in that it activates the sense amplifiers as well as the row decoder. CAS is used as a chip select, activating the column decoder and the input and output buffers. Right. So we've basically got 2 latches. I'm sure I can do this. Add a circuit. What was that calling it? It was the NTE 4164. Shouldn't really be in the 7400 series though, should it? So let's open a new one because I need to start a completely fresh one. New. Okay. Close that one off now. Okay, so we've got add a circuit NTE 4164. Let's load a library of my 7400 series. Right, so we've got 2 latches. Um, 244 is it that I want? No. 245, what have we got here? No, that's bidirectional buffer. I'm sure I have 273. 273. Okay, a pair of 273s. That for row and that for column. Okay, pins. A0 to A7 we need here, which connect through to both. All the inputs to these come from the address pins. A1, A2, A3, A4, A5, A6 and A7. Connect up all the column address pins. A6 and A7. There's no clear, so that will go to a constant 1. Excellent. Right. So now I have two more pins. That one there is RAS. This one here would be CAS. Okay. That then gives us our 16 address lines. I'm going to do a fan out on these, I think. Splitter. Fan out of 8 with a spacing of 2, facing west. With 16 bits in. And I need 0, 1, 2, 3, 4, 5, 6, and 7, with all the rest none. Okay, copy this. And have it as these are all none. And these ones, 8 to 15, are on 0 to 7. Okay. Now I've got a date address bus there. Let's save this now as memory. The file name may not be equal to a circuit name, tool name, or library name used in your project. The specified file name equals to one of these names. Oh, there's a library there called memory. I'll call it RAM then. No, there's a DRAM. There we go, DRAM. That works better. Right. So now I could go for a RAM block here. Address bit width, I can now have as 16. Data bits, I only need one. So address can then go straight into here. This is synchronous, this, isn't it? Memory value updates on a rise from 0 to 1. So load memory to output on when was it? It did specify, didn't it? RAS is similar to a chip enable, activates this blah blah blah. CAS is used as a chip select, activating the column decoder and the input and output buffers. The 3-state output buffer provides direct TTL compatibility. Blah blah blah. Data out is the same polarity as data in. The output is in the high impedance state until CAS is brought low. So CAS being low is the same as output enable. So if I take my CAS signal here and put that into output enable, it wants to be inverted. Gates, not gate. Okay. Let's put a pin on here, shall we? West facing, yes, it's an output, yes, it's 3-state. That is VO. Right, and write enable. The read or write mode is selected through the write enable input. A logic high on the W input selects the read mode. Right, so that can only be output enable when M3 is when write is high. So I need that to be high and right. So I'm going to need an and in here. Let's shrink that. So output enable when write enable is high. Okay. And if I were to connect that and that to an inverted, no, let's take that lot out. If I connect write enable to C1 and not gate here on write enable going to there with a pin here for input. Okay, let's see what happens with a 1 going in here. Right enable goes low, right enable goes high. No. Why am I getting an error here? I'm not sure what this... that normally means that it's connecting to an input rather than output. Let's just see if this does anything here. That certainly changes the address here, doesn't it? I'd expect that to change. Right, that has changed. We now do that. To a 0. Does that go to a 0? That goes to a 0. That goes to a 1. Okay, so that's operating on the input. That connected to there. Right, that's working now. Maybe it's just because it had never actually had an address input. So that should be giving me a 1. It's not. Because CAS is high, that's why. Output enable. That's on there as well. That's better. Right, we've got proper address in there now. So I write a 1 to that. That is set to 3 state, yes. Okay. RAM type volatile enables. Use line enables. Enables. Not sure what this means. No clear pin. I want it a low level. Right, so that's not needed now. Neither is that. So right enable now is taken straight from here. Okay. Why is that not giving me anything on? That must be on and that is on. as soon as I do that, output enable, that should go that should go high impedance. But why isn't it? Separate data bus. Anybody ever used VRAM in Logisim before? Why doesn't that go high impedance? I mean, I can add my own buffer to it to fix that, but it should go high impedance, I'd have thought, since it's got an output enable. Let's put that up to 1. That goes on now. That's giving me my output there. But as soon as I do that, it goes down. I can't have that doing that because that's going to be looped back onto the same bus. Why is that like that? I'm just going to add my own buffer in there. That's the simplest option. Control buffer. Okay, that comes from output enable being high. So now it's undefined. As being high should be undefined, yeah. I need this to be and I need that also to be on CAS and RAS. I'm not entirely sure, or at least on CAS. Actually, what I'm going to have here is not a not gate. I'm going to have instead moving my RAS down here as well, and have here a NAND gate. Which will be low when both CAS and RAS. Although CAS, no. I don't know, because RAS is only pulsed. CAS is activate. So no, I don't want that, do I? No. Let's get rid of that. I do want a not gate here because I need this to be when low. So I want that when low, but I also think I want that. Hang on, this is yeah, that's set to a low level, that isn't it? So this needs to be that needs to be right. No, this needs to be low. That needs to be low. So yes, I want to bring let's put this up here where it was. That wants to be on the input to here. I need this to be low. I need the right to be low, which means I need that to be an OR gate. So that if either is high, it goes high. Let's make that narrow. So I've got that needs to be low and that needs to be low for that to be low. Right. So I think I've got that now. Okay, so let's look at the logic of this. We've got write enable is high, CAS is low. I've got D0 showing. Yes. Write enable is low. My data gets fed in. DO is undefined. Write enable goes high. CAS is still low. DO goes to mirror my data. CAS goes high. DO is undefined. Write enable goes low. Let's put that to 0 so you can see a change. Write enable goes low. Nothing happens. Excellent. I think that has got it. I think I am set for the round chip. Okay, these are in a bit of a mess, these. Let's go back to the layout. I'm going to move the position of these matters. So let's move CAS up to here. Let's move write enable up to here. Let's move data in up to here. And go back to the appearance and regenerate it. That's better. Data in, write, CAS, RAS, addresses, data out. Happy with that? I think now I have done all the chips that I need for this tangled mess of a circuit. It's also only a partial circuit, which doesn't help. And some of the labels are missing, which is why I want to put it into Logisim so that I can work out what the missing labels are and what the functionality of all the parts is. Basically, this circuit is the memory controller for I think it's a compact portable, possibly. It's based on the schematics of the IBM 6150 or 60, I think. And this is just the memory controller portion of it, which was having an expansion added to it. And the expansion wasn't being detected and used properly, so we need to fathom how it's communicating, how it's all set up, what the jumpers do, all that sort of thing. There's no documentation for this. So I'm taking at least this partial schematic and trying to fathom how it operates. So, yeah. I suppose my next job is to create this circuit in Logisim. And this part of it here has just been done as a shorthand. We've got 4 RAS pins, 4 CAS pins, so there's going to be 4 banks of chips and 8 in a bank. 9 if there's parity, actually. There might be parity, I can't remember. But you've only got 1 shown in this schematic. One, two, three, 4 for those. We've actually got an A8 pin here, which is the larger chips, which is coming from 16 or 17, depending on the state of this mux here. And there's nothing there to say what that mux is. Okay, that's... I'm going to need to know what those are before I can do anything. Right, okay, so I can ignore that for the moment. And let's work on the RAS and CAS stuff here. So we have a 157. Can we? Yeah, let's. No, that doesn't do anything, does it? Oh, there we go. That's. Ugh. I can rotate it, but I can't flip it. Come back. Where are you gone? Okay, so we have A, B, C, and D here. A and B go to RAS 2, RAS 3. And over here we've got more. So A is RAS 1. I shall have this coming around to RAS on here. B is RAS 2. Okay, RAS 3 comes from right back here. RAS 0 and 1. Oh, hang on, that's RAS 2 and 3, sorry, my bad. That should be going down to RAS there. Going down to RAS there. And got RAS 2 and 1 come from further afield. RAS 1 and 0, I mean. That's RAS 1 there, that's 0 there. Okay. RAS. These are the opposite way around, aren't they? A is actually RAS 3. 2 there, and that's ras 3 there. So we've got ras A is ras 3. That's ras 2 there. Okay. C goes to cas 3. D goes to cas 2. Put a label here. This is cas 3. This is ras. Oh, sorry, cas 2. So the lower one here is cas 3, which goes all the way down here. Cas 3. Cas 2 comes up here. Yeah, I've got this the wrong way around here. I want to have these the other way. Pull that in that way and push that out that way. That's better. And that goes up there. So we're going to have to move across, aren't they? To make room for the other cas pins. Pull the rases over. Cas 2 and cas 1 and cas 0 here. Okay, pull these out this way. Those come from, again, somewhere else. They come from these AND gates. So this is cas 1, cas 0. Put some labels on. Right. We've got this bit here I queried and it is wrong. So I can't do that bit yet. So let's put in some AND gates then. Facing west. 2, 3, 4, and a gap. And 4 more. No, 2 don't really go anywhere. Right. Come back. Move the whole lot down. Okay, so the top one here goes into input 1C. Which C1 here. The second one goes to input 1D. Which is that one. No, that's D. Yeah, D1. Okay. The third one goes to CAS 0, which is up here. And the fourth one goes to CAS 1. Okay, that's those outputs done. Then I've got these two here. The top one goes to input 0D. 0D is there. Second one goes to 0C. Let's move that across one. Okay. The lower inputs of all 6 of these are tied together. And that comes from another NAND gate here, which is all sorts of complicated things. The upper ones come from this 138. So let's put this 138 in, shall we? 138. I mean, this whole schematic really is backwards. It should be round the other way. Because all the inputs are on the right and all the outputs are on the left on all these chips. I mean, it might be worth actually taking an image of it and just mirroring it left to right, so that all the gates, all the chips and everything are all oriented in the right direction. Because it's completely left to right at the moment, which is not good. So it means that all my traces are going all over the place. So anyway, output 0 goes to the top one. I might rotate this one, it'll look ghastly, but output 0 goes to the top one, output 1 goes to the next one down, and so on and so forth. Like so. 4 to 7 aren't connected. Here I've got a 139. Got 139, haven't I? Yep. Let's rotate that as well. Output 0 goes to the bottom one. YA0 goes down to here. And YA1 goes to here. Okay. '91, 92B, 90. So that's also the same one as this here, isn't it? So that's the B's, which I'll have going up to there, which go to inputs So output 0 of B I shall have coming to input 0A on here, A0 here. Okay. Goes all the way, snakes its way around to there. Output 1 goes to B0. Snake that along next to it. 1 goes to there. Okay. The 1 inputs to that mux come from a 138 over there. Okay, 138. So we've got 0 goes to RAS3, which comes into input 1A. Input 1A is this one here. I'm going to go up for these, I think. 0, 1. So input 1B can come along here. So 1A goes to 0. 1A goes to 0. 1B comes along here and goes to 1. Goes to 1, okay. 2 goes to RAS1. And 3 goes to RAS0. RAS1. And RAS0. We're making progress here. Okay. Let's save this, shall we? Save this as memdebug. Ooh, I think my brain is melting. I think now that we've got the RASs and the CASs both connected up to their respective sources, I think I'm going to leave it there for today. I think I've done enough. It's the kind of job where I'm going to have to just do a little bit at a time every now and then because it just melts my brain trying to trace all this lot. So I'm going to call this test of my new streaming system a complete success. I shall see whether it's actually done all its recording and things in the background that it should be doing. I forgot to start my audio recording, didn't I? But meh, whatever. Let me just run that now and see what happens. I've got all my inputs going. That seems to be recording fine. I don't need my recording for this one. I'm not going to be actually using this as a source for putting together a video, so meh, whatever. It's something I must remember to do, though, is start my audio recording. But hopefully it's done everything else, and I'm going to leave it there. I'm going to say goodbye, and thank you for joining me. If you enjoyed it, excellent. See you next time. I don't know when that'll be. I need to do more of these sort of stream while I'm working kind of things, just to get my stream quantities up. Right, well, see you later. Cheery bye.